Hi everyone, this is Akanksha and welcome to our Mechanistic Interpretability 101 playlist. This is the second episode where we are going to talk about probability, statistics, and information theory. So my idea to explore all these math concepts before we get into the machine learning side of things is to get you comfortable with the math part. My main goal here is to remove any fear of math that you may have by allowing you to see math in a new light, in a fun light. So let's get started. If you're on social media and if you're into memes, I'm sure you have seen a version of this kind of a meme. Still waiting for the day when I will use math in real life. I'm sure you are here because you want to learn math, and the fact that you clicked on this video means that you're committed to learning it. It does make the learning more fun and doesn't seem like a mammoth task when we realize that we indeed use this math that we're going to learn today in our day-to-day lives. So I'm not going to give you the boring rain and umbrella example to talk about probability in our day-to-day lives. Instead, let's talk about food. Who doesn't like food? I am definitely Joey from Friends when it comes to food. And I assume you two are. So I'm guessing you dine out every once in a while to enjoy food. And we are going to use that as an example to learn probability. And I hope this example won't backfire me and push you to close this video and run for food. So, how do you select the restaurant when you want to eat out? Most likely you Google it, or if you're great at adapting to tech, maybe you are now asking ChatGPT, but basically you explore a variety of options. You might want to select one that is having good reviews, or perhaps you choose a place because one of your friends raved about it. So if you usually enjoy Italian food, you might estimate a higher probability of liking this new Italian restaurant that came up in your Google search. Or maybe the restaurant has a cool boho vibe, so you're more drawn to going there. So this part where you are attracted to a certain option more than others is where your brain is assigning a likelihood to the outcome of your experience based on prior knowledge of what you usually enjoy and the current information you're feeding it. So our brain is casually using math and doing all the calculations to find out the exact probability of us liking each one of these options and giving us a decision based on the restaurant choice that got the highest probability score in its calculations. Now, one of the reasons we can consider while assigning this probability score might be a friend's recommendation. And let's say your friend has suggested these 5 Italian restaurants to you in the past, and you have liked 4 out of 5 of those recommendations. So you might be inclined to consider her recommendation again. This part here is your brain deciding to assign a certain probability score based on the statistical analysis of 4 out of 5 being a good call. So you're using the frequency of past events to predict the future outcomes. And now let us consider the most difficult part. You might have found 2 boho Italian restaurants, and now you're confused about the final decision. At this time, you will consider the reviews and the average ratings for both of these restaurants, or maybe you'll call up your friend and ask if she has been to any of these, or you might check which one is closer to your place. And if you're someone like me, maybe you'll just check which one has the better dessert menu. By gathering more data, your brain is basically trying to reduce the uncertainty about what to expect and help you make a more confident decision. This is similar to reducing entropy in information theory, and we will learn about all of these in detail now. So you might not have realized, but us humans make decisions every second of our life. Our brain is not only making decisions like where to go to eat, which movie to watch tonight, or where I want to go for work after I graduate, and how will I apply to this company, but it is also making all the other decisions pertaining to things like maintaining our body temperature, when to raise our heart rate, when to relax, and various things like that. It is all decision making, constant, tireless decision making. And that is exactly what our machine learning models have to do. And while our human decision making is sometimes based on pure logic, or sometimes on past experiences, or sometimes purely on emotions, the machine learning model's decision making is based on pure math. So be it Netflix's movie recommendation, or Instagram's reel suggestion, or cancer detection, or calculating the fastest route on Google Maps for us, machine learning models are using the rules of probability, statistics, and information theory. And let's say you're talking to ChatGPT or Claude. Each word from its reply is also based on these exact same rules. So take a moment and realize this. We may not be able to understand and decode how our human brain works, but learning these topics in detail will definitely help us decode the core of machine learning models' decision making. And that's definitely a wow feeling. So let us begin exploring the depths of probability. For starters, let's consider this example. Let's say we're solving a quiz, and that is a question that is asking us to check if a statement is true or false. Let's say the statement is Zluto is a fruit. There are only two choices we have. We either have to select true or false. And just like you, I haven't ever heard the name Zluto. So we have to make a random guess. And because we have no idea about Zluto other than the fact that it rings like Pluto, there's a 50% chance that we will guess true and also a 50% chance that we will guess false. This is expressed mathematically as shown here. So probability of the option being true is equal to number of favorable outcomes upon total number of outcomes. So that will be 1 upon 2 because total number of outcomes is 2 and the number of favorable outcomes is 1 here because being true is a single case. So we get P of true is 0.5 and similarly P of false is 0.5. So each choice has a 50% probability as seen before. And this is the formula we use to calculate probability. Remember that probability is a mathematical study of processes that involve any kind of uncertainty. And another key thing to remember here is that the value of probability is expressed in the range of 0 to 1, where 0 indicates the event will not happen and 1 indicates that the event will most definitely happen. So let us quickly see what the basic rules of probability are. The first one, rule of non-negativity, says that probability that Zluto is a fruit or that it's not a fruit must be between 0 and 1. Neither can be negative. The rule of total probability says that the only two possible outcomes are true or false. Since these are the only possibilities, their probabilities must add up to 1. Complementary rule says that if the probability that Zluto is a fruit is P of true, then the probability that Zluto is not a fruit is P of false equal to 1 minus P of true. The addition rule for the disjoint events says that Zluto cannot be both a fruit and not a fruit at the same time. Hence, we see this kind of equation. The multiplication rule says that suppose you have to answer two quiz questions like is Zluto a fruit and is Lumo a fruit? And if these questions are independent, meaning knowing the answer to one doesn't affect the other, then the probability that both are true is calculated like this. Now let us understand the conditional probability rule. Suppose you learn that Zluto comes from Amazon region. So if A is the condition that Zluto is a fruit and B is the condition that it comes from Amazon, then the conditional probability tells you that Zluto is a fruit given that it comes from Amazon. Now coming to the law of total probability, if Zluto could come from one of several regions, each with different probabilities, the law of total probability would allow you to calculate the overall probability that Zluto is a fruit by considering the probabilities that Zluto comes from each one of those regions and then the conditional probability that it's a fruit given that region. So this is how that is calculated. Now let's consider Bayes' theorem. Suppose you learn that Zluto sounds like a fruit name 80% of the time, and generally only 10% of unknown names are fruits. You could use Bayes' theorem to update your belief about the probability that Zluto is a fruit given that it sounds like one. And we use this equation to apply Bayes' theorem. Now let's consider mutually exclusive events. If knowing whether Zluto is a fruit doesn't affect the probability of another event like Lumo being a fruit, then these two events are independent, and this is how we calculate their probability. And now let's consider the example where event A is Zluto is a fruit and event B is Zluto is green. These events are not mutually exclusive because Zluto can be both fruit and green. In this case, the general addition rule applies where P of A intersection B is the probability that Zluto is both a fruit and green. Now let's go through some of the most widely seen probability distributions. So in uniform distribution, consider random initialization of weights in neural networks. When initializing weights uniformly, each possible weight value has an equal probability of being chosen, leading to this kind of a uniform distribution. Predicting the number of successes in a sequence of independent binary, that is yes-no experiments, such as determining the number of emails classified as a spam out of a given batch, can result in this kind of a binomial distribution. Now let's consider a single trail in the binary classification problem, where a model predicts whether a given input belongs to one of the two classes, such as a model predicting whether an email is spam, that is 1, or not spam, that is 0. That's where we see this kind of a Bernoulli distribution. Now you must have seen this kind of a graph a lot of times. It is sometimes called the bell curve due to its bell-like shape and also known as Gaussian distribution named after the scientist Carl Gauss. Consider the example of plotting a distribution of average score students got in a subject. Most of the students will be around average and there will be less number of students who would have topped the exam and less number of students who would have failed the exam. Many machine learning models assume that the errors or noise in the data are normally distributed. For instance, in linear regression, the residuals, that is, the difference between the observed and the predicted values, are often assumed to follow a normal distribution. Now, let's consider the example of modeling the distribution of income generation. So you can guess that it involves compounding factors such as investments, promotions, or interest rates. So when you take logarithm of this kind of a variable resulting from such a multiplicative process, it often transforms the data into a form that is normally distributed. And finally, let's consider negative and positive skew. When applying data features, you may find that the distribution of a particular feature is skewed. For example, in housing price prediction, house prices might be positively skewed, meaning most houses are moderately priced and very few are expensive outliers. So these kind of distributions help model different types of data and assumptions in machine learning, guiding the selection of appropriate algorithms and techniques. Now let's learn Bayesian inference. It is a method of statistical inference in which Bayes' theorem is used. It is used to update the probability of a hypothesis as more evidence or information becomes available. It's essential in machine learning for updating models in light of new data, making predictions more accurate over time. So let us understand with an example. Bayes' theorem is mathematically expressed as this, where P of H given D is the posterior probability, that is, the probability of hypothesis H given the data D. And P of D given H is the likelihood, that is, the probability of observing the data D given the hypothesis H is true. P of H is the prior probability, that is, the initial belief about the hypothesis before seeing the data. And P of D is the marginal likelihood or evidence, that is, the total probability of observing the data D under all possible hypotheses. So let us consider the application of Bayes' theorem to find out whether an email is spam or not a spam. So consider that hypothesis 1 is email is spam and hypothesis 2 is email is not a spam. Then P of H1 is the prior probability of email being spam. And let us consider that probability to be 20%. And P of H2, which is prior probability of email not being a spam, is obviously going to be 100 minus 20, that is 80%. So let's consider that the probability of the word lottery appearing in a spam email is 70%. So P of D given H1 is 0.7. And let's consider that the probability that the word lottery appears in a non-spam email is 5%. So P of D given H2 is 0.05. Why so low? Because we are considering all of the emails and we are trying to see how many times lottery appears in those. So that is going to be very less. So now P of D, that is the marginal likelihood or evidence, meaning the total probability of observing the data D under all possible hypotheses, is found out using this equation, and that comes out to be 0.18. And now the posterior probability P of H1 given D is the probability that the email is spam given it contains the word lottery. And using this equation, we get that there is a 77% chance that the email is spam given the word lottery in it. So before seeing the word lottery, we believe that there was a 20% chance that any random email was spam. After seeing the word lottery, our updated belief now says that there is a 77% chance that the email is spam. This shows how Bayesian inference allows us to update our beliefs in light of new evidence, as we can see in this graph. Bayesian inference has wide applications in practical machine learning tasks such as spam detection, recommendation systems, and more. Now let's consider Markov chains. A Markov chain is a mathematical system that undergoes transitions from one state to another within a finite or countable number of possible states. It is characterized by the Markov property, as we can see here, which states that the future states depend only on the current state and not on the sequence of events that preceded it. Let us consider a simple example where we use Markov chain to model weather prediction. Suppose S1 is sunny and S2 is rainy. Now assume that the weather follows a Markov chain represented here. So if it's sunny today, there is an 80% chance that it will be sunny tomorrow, and a 20% chance that it will be rainy tomorrow. And if it's rainy today, there is a 60% chance that it will be rainy tomorrow, and a 40% chance that it will be sunny tomorrow. These probabilities can be represented in the transition matrix P as shown here, where the first column represents tomorrow being sunny and the second column represents tomorrow being rainy. Our initial vector V0 is given by this equation. This means that there is a 100% probability that it is sunny today and 0% probability that it is rainy today. So to predict the weather for tomorrow, that is one step ahead in our Markov chain, we multiply the initial state vector V0 by the transition matrix P. And this is the result that we get. So this result tells us that there is an 80% chance that it will be sunny tomorrow and 20% chance that it will be rainy tomorrow. To predict the weather for day after tomorrow, that is two steps ahead in our Markov chain, we multiply the result V1 by the transition matrix P. And this is the result that we get, which indicates that there is a 72% chance that it will be sunny day after tomorrow and 28% chance that it will be rainy the day after tomorrow. So this is how we can make predictions using Markov chains. And these are used in various machine learning applications. So hidden Markov models are used in modeling tasks like speech recognition, and Markov chains are also used in generating text by predicting the next word in a sentence based on the current word. Now let's move on to statistics. Mean, variance, and standard deviation are the key statistics that provide insights into the data's central tendency, spread, and overall distribution, making them essential tools in both statistics and machine learning. The expected value, also referred to as mean of a random variable x, is an average value of repetitions of the same experiment. In other words, it is a weighted average of all possible values that x can take, and each value is weighted by the probability it appears in an experiment. So these are the formulae which are used to calculate the expected value of a random variable x, or an arbitrary function g, or a continuous random variable x. Now coming to variance, it is the expectation of squared deviation of all possible values of a random variable from its mean. So in other words, it is a measure of the dispersion of the possible values of the random variable around the expected value. The variance is often written as var, and var of x here represents the variance of a random variable x, and it is given by this equation, where mu is our deviation. And now coming to standard deviation. It is a measure that tells us the dispersion of all possible values of random variable x from its mean, and it is calculated as the square root of variance, and it is denoted by sigma of x. Let us understand all these concepts in detail with an example of housing price predictions. So as you can see in this plot, the blue line shows the predicted prices for 5 different houses. Now, how will we calculate the expected value, that is mean? We calculate it by averaging all the predicted prices. And this is what we get. So $315,000 is our expected value or mean, which is shown by the red dashed line here. The green dotted lines here represent the deviations of each predicted price from this mean. These deviations are used to calculate the variance, which measures how spread out the prices are from the mean. So using the formula for variance, we get this value. And using the formula for standard deviation, which is just the square root of variance, we get this value. So as you can see here, there are two oranged dot dash lines representing the standard deviation. So one is $10,000 above the mean and one is $10,000 below the mean. So here the mean of 315K gives us a central value around which the predictions cluster, and the variance and standard deviation can describe the spread of these predictions. So a lower standard deviation would indicate that the prices are much closer to the mean, implying more consistency in the model's predictions, whereas a higher standard deviation suggests greater variability, meaning the model's predictions are more spread out. So these were the 3 most important concepts in the topic of statistics. Now let's move on to information theory. Let us start by understanding the concept of entropy. Entropy is a unit of information. What do I mean by that? Let's consider this example. As shown here in this figure, consider that there are 3 baskets, basket A, B, and C, and each of them have some blue balls and some yellow balls. So the chance or probability of picking a yellow ball from basket A is given by x is equal to 0.1. So the entropy h of x then is given by this formula, and this is the value we get when we solve this equation. So now the chance of picking a blue ball from basket A is 0.9. As we can see, there are 9 blue balls here. So given P of y is equal to 0.9, the entropy h of y is given by this formula, which results in this value. And because entropy is a unit of information, it is represented in bits. So we say that the entropy of the system of the decision of us picking a ball from the first basket is given by 0.469 bits of entropy. Now let's look at the concept of cross entropy. For 2 probability distributions where P is the true distribution and Q is the predicted distribution, the cross entropy H, P, Q is defined by this equation. Let us understand the concept of cross entropy by looking at this plot, where blue is the class 1 probability and pink is the predicted probability. So true distribution where the true class, that is class 1, has a probability of 1. Now, prediction Q1 shows the predicted distribution is close to true prediction with a very high value of 0.9. And that's why we get a very low amount of cross entropy using this formula. The lower the value of cross entropy, the more accurate the predictions. And in prediction Q2, we can observe that the predicted distribution is uncertain, assigning equal probability of 0.5 to both classes, which is why we get a very high value of cross entropy given this formula, which reflects that the predictions are very less accurate. And in prediction Q3, the predicted distribution is incorrect, assigning a high probability 0.9 to the wrong class. The cross entropy is the highest of value 3.32, indicating very poor predictions. So overall, lower cross entropy as seen in Q1 indicates that the predicted distribution is close to the true distribution, meaning the model is making accurate predictions. and higher cross entropy as seen in Q2 and Q3 indicates that the predicted distribution diverges from the true distribution, meaning that the model's predictions are less accurate. So in classification problems, cross entropy is often used as the loss function to evaluate how well the predicted probabilities match the true class labels. It helps the model adjust its parameters to minimize the difference between the predicted and the actual distributions, leading to a better accuracy. Now let's look at another important concept, the Kullback-Leibler divergence, also known as the KL divergence. It is a measure from information theory that quantifies how one probability distribution diverges from the second. And this is how it's mathematically represented. So let us understand the concept of KL divergence by looking at this plot, for example. Here, it shows the comparison between the true distribution P and the predicted distribution Q for a binary classification problem. Here, the light blue bars represent the true distribution of where the true probability of positive class is 0.8 and obviously the negative class is 0.2. And the light pink bars show the predicted distribution of Q, where the model predicts the positive class with a probability of 0.6 and of a negative class with a probability of 0.4. So now we calculate the KL divergence using this formula and get this resulting value. The KL divergence value of 0.0915 indicates that there is a small but non-zero divergence between the true distribution and the predicted distribution. This means that the model's predictions are not perfectly aligned with the true distribution, but they are relatively close. A lower KL divergence value suggests that the predicted distribution is closer to the true distribution, indicating a better model performance. If KL divergence were to be zero, it would mean that the predicted distribution exactly matches the true distribution. KL divergence plays a huge role in machine learning algorithms, including generative and reconstructive models such as variational autoencoders. So consider this latent space that is representing the numbers 0 to 9, and the yellow dots are representing the number 1, and the purple dots here are representing the number 7. So how would a value that is falling in between both of these numbers in this empty space be represented as? It will be something messy and not look like either one of them. And there is no KL divergence applied here. So when KL divergence is not applied, it looks like this, where there are big empty spaces between the classes. So when we use KL divergence, this is what we get. There are no big empty spaces between the two classes, giving us a chance to represent the number that falls between them in a much better way. So that's how KL divergence helps us. So that's the end of today's session. Just to revise, we explored the concepts of probability, statistics, and information theory through that restaurant example and just had fun with it. Then we checked the rules of probability. Then we saw the different probability distributions and their applications, concepts of Bayesian inference and Markov chains, the concept of mean, variance, and standard deviation. We explored entropy, cross entropy, and KL divergence as the part of information theory. So I hope that this brief overview gave you a good grasp on all these concepts. And I'm very sure that understanding all these concepts is going to be very helpful tomorrow when we are going to decode neural networks. In the next session, we are going to tackle the mighty topic of calculus. And once we understand that, there's no stopping us. So see you in the next session. Cheers.